Hello and welcome to my presentation. My name is Saif Saleh. I am a PhD student at Auckland University. I'm working under supervision of Professor Richard Alawian, Department of Industrial and Systems Engineering, and here is the topic of my presentation: Intelligent Performance Analysis of Automated Steering Systems for Autonomous Vehicles. Some outlines of my presentation here. I will start off with some background information of autonomous vehicles. Then I will talk about the autonomous steering system architecture. Then I will talk about the test methodology of this research and the data collection from the bench and give some result. And then I will end up with some conclusion. Talking about the background of autonomous vehicle, the Society of Automotive Engineers, uh, SAE, defines the level of autonomy into 6 categories or 6 levels. Level 0 represented that driver only is in charge of controlling the vehicle. There is no any assistant from the system. The system has nothing to do with the control of the vehicle here. Moving to the highest level of automation or autonomy, it's called fully autonomous vehicles or driverless vehicles, where is no driver even presented in the vehicle. This technology or level 5 requires the machine fallback, and from functional safety standpoint it requires the fail operation because there is no driver in the vehicle, so the machine is fully responsible. I mean, when I say the machine is the control system of the vehicle is fully responsible for controlling the vehicle, the lateral and the longitudinal control of the vehicle. The technology now is level 3 and we are moving to level 4 as reported by most of the OEMs. Highly automated vehicles where the vehicle can control the longitudinal and the lateral control of the system. The control of the vehicle can control longitudinal and lateral control of the vehicle, but if there is any fault or malfunction in the system, it will report to the driver, so the driver can take over the control of the vehicle. But according to the OEMs, by 2025 or 2026, we will have level 5, the fully autonomous vehicle or driverless cars or vehicles presented in the market. And again, this requires the machine fallback and the fail operational mode from functional safety standpoint. So here is a comparison between steering assist and steering actuation. So in steering assist, the system is assisting the driver. The driver must be presented in the vehicle and paying attention to the road all the time, but the system is assisting the driver by the ADAS concept. And but when we said fully autonomous vehicles or driverless vehicles or cars, there is no driver presented in the vehicle, or the driver may be involved or doing other activities in the vehicle. So the autonomous system or the control system of the autonomous vehicles is fully responsible for the controlling the vehicle laterally and longitudinally and maintain the vehicle path. So there is no driver presented in the vehicle here. Again, there is here's the comparison between electric power steering system versus the autonomous steering actuator. And the most important thing of this is the controllability of the system. So the autonomous vehicles requires the system to be fully responsible from controllability standpoint of the vehicle. But here in the EPS or the electric power steering, the driver must be presented and the system is assisting the driver. And if there is any malfunction or any failure in the system can inform the driver and hand over the control to the driver. The challenge of artificial neural network and artificial intelligence in autonomous vehicles. So we are moving from the traditional system control concept whereas the ASIC, application specific integrated circuits, or the FPGA, the field programmable gate array, here the embedded system control microcontrollers, we are moving towards artificial intelligence, where the artificial neural network will control the system, will control the vehicle. This traditional or conventional embedded control is a programmable math model that controls the logic gate. So when it has the input, it will actuate the output, and it has some feedback from the output to the input. But the artificial neural network has no feedback. It's called feed-forward control concept, where the input layer receives the data from the sensors, and it connects the data to the hidden layers, and then this hidden layers will train or predict the patterns of these data, and then it will control the actuators from the output layer. And as you see here, the artificial neural network does not have feedback. There is no feedback from output to the input. It's called feed-forward concept of control. I use the neural network training toolbox of MATLAB to train my model and to predict the output. And the output is, I will talk about the output in the next slide. So the test methodology of this research, I collected some data from the DSpace hardware in the loop high fidelity bench. I collected, it's a fully virtual environment for the vehicle and for the environment. I collected the vehicle speed and the steering wheel angle and the steering wheel speed and the steering column torque. The most important parameter here is the steering column torque, because I will use this parameter to validate my artificial neural network against the output of the bench, as I will show in the next slide, and then I will compare them to see the performance of artificial neural network. Because the steering column torque is controlling the vehicle laterally. And as you see here is the topology of my bench. I use the ASM and the DSpace. It's automotive simulation model. I use these applications to collect the data and control the vehicle. And within that, I use a lot of CAN channels and a lot of protocols to collect the data. And here is the source of my data. The output of my artificial neural network training and validation, I built the artificial neural network in that toolbox of MATLAB. It's called artificial neural network training toolbox. I put these data here, the data that I showed in the as an input to the artificial neural network, and I used the steering column torque to validate my artificial neural network. So the target here, the x axis here, is the collected data, the collected steering torque, steering column torque from my bench, and here the y-axis is the output of my artificial neural network. I use the regression concept to compare both. So the regression of 69.2% represent how well or what is the performance of my artificial neural network against my target. So there is a deviation of 3.7 between the target or the steering column torque of my bench and the output of my artificial neural network. And most of these deviation showed up in the extremes values of steering column torque. And this is due to the behavior of vehicle dynamic with high number of degree of freedom, DOF, and the nonlinearity and the complexity of these parameters, the vehicle speed, the steering wheel angle, the steering wheel speed, and uh, um, the input, that they are not linear, they are not related to each other, but the artificial neural network took these data, compared them, and then trained the model to be as close as to the target of the steering column torque. This is the training, and this is the validation. And as you see, the errors increases at the extremes. The positive is the right side of the torque, and the negative is the left side of the torque. From computational standpoint, so that the model, the artificial neural network model, uh, um, at the epochs of 132, it gives the as least, or it gives the minimum error, the minimum square error. Uh, so we would like to see the minimum square error 0, but the model here, the best validation performance of the artificial neural network at this epochs 132, it gives the lowest number of error here. And the time, I think it took 50 seconds to validate or to train the data. Again, here is the error histogram of the artificial neural network that showed up here. I have 20 pins here, and to have the lowest mean square error, the model needs instances, 3000, maybe 400 instances, or the data set combination of these input, so it can have the lowest number, or the lowest mean square error. And if you see here, the blue is the training, the green is the validation, and it tests the data set, the red here. So again, the error is the target minus the output. So I would like to see 0 error here, but it is I mean it's showing some error here, and this is again due to the complexity of these parameters, because they are not related to each other, and the dynamic behavior of the vehicle, given the fact that it has high level of degree of freedom. So the conclusion of my research here is the architectural challenge for artificial neural network and autonomous drive. So autonomous driving, or autonomous vehicle deployment, it is happening very fast, and it's happening earlier than we think. Maybe by 2025 we'll have fully autonomous vehicles in public. The field operational steering is required for autonomous vehicle from a functional safety standpoint. There is a parameter I use. It's called wheel speed, or steering wheel speed, or steering wheel rate, which is degree per second. This is rarely used in the market now. It showed it's clear that it is a key role in autonomous vehicles, especially when it comes to training and predicting the pattern of the autonomous vehicle steering. So this is a very important parameter that OEMs and steering system developers they need to involve it in the control system of autonomous vehicles. The regression of 96.5% versus the measured steering torque commands was achieved by this research. So there is a 3.5 deviation at the end, or at the extremes value of the steering torque command. The artificial neural network can effectively predict the steering commands, and given the fact that the non-linearity and the complexity of the steering system, and I mean, there's a recommendation from this research to use the artificial neural network as an abstraction level of in the control system of the autonomous vehicles. that will enhance the predictability and controllability of the steering system of autonomous vehicle. If there is any question, please ask, and I will be more than happy to answer. Thank you.